So the next speaker is Professor Ying-Jer Kao from Taiwan, and he is going to talk about this tunneling-induced restoration of classical degeneracy in quantum Kagome Ice.
Hello? Okay. So first of all, I'd like to thank the organizers, including myself, but it's mostly Subhro, for this wonderful workshop. And so what I'm going to tell you is a story that was puzzle us for a long time, and I think we understand what's going on in this system. So we've heard about a lot of this spin liquid stuff, but what we find is actually a classical spin liquid in a quantum model. Okay, so I'm going to tell you the story, and this work is done in collaboration with my student Kai-Shin. He's in the audience, and Yiping Huang at the MPI PKS. Yeah. So this is a show online. So I'm going to introduce you what spin ice. Arnab yesterday gave a very nice introduction of this spin ice physics, and I'm going to talk about Kagome Ice, and I'm going to show you some of our QMC results and some of this Degenerate perturbation theory results, and give you some conclusions. So spin ice, if you have a magnetic moment which is confined in the local 1-1 axis, so they can only point in or out, then you realize that if you have a ferromagnetic interaction, the lowest energy ground state for each tetrahedron will be just 2 spins pointing in and 2 spins pointing out. And for each tetrahedron, there are 6 degenerate configuration with 2 in, 2 out spins. And this is a so-called ice rule, and the name comes from because this is very similar to what happened in water ice. You have for each oxygen ion, you have 2 protons coming in and 2 protons moving away from these oxygens. And Pauling estimated this residual entropy because of this degeneracy. There's a residual entropy due to this massive ground state degeneracy, and this is the number. And so in a spin ice system, it's possible to measure that and confirm this missing entropy, as Arnab showed yesterday. Okay, and also here. Sorry. So what was shown here is the dysprosium titanate data. If you do this integrated the specific key peak, and what you find is that at high temperature, you expect the system to have this log 2 per. Because it's in a paramagnetic state, but there's a piece of an entropy is missing, and this missing entropy is very close to what you expect in the from this Pauling estimate. Okay. So what I talked about before are just all classical, because you have Ising spins and you have you can turn on interactions. You have an exchange. You can have a dipolar interaction. But the interesting thing is you can also turn on quantum mechanics. Okay, so to model the system for the quantum spin ice systems. Initially, people focus on this ytterbium titanate. Okay. This is a Kramer's doublet, and this is the minimum model you can write down in terms of this in terms of this doublet. Okay, so this is a effective pseudo spin 1/2 model, and you can think of you have this classical piece, but you have all these different. This is a hopping piece, and also this piece is coming from this single ion and anisotropy. Okay, this model has been studied extensively and by various methods, and there's a nice correspondence between the model and the experimental results. So people can nail down all these parameters. But there's a problem because if you want to throw this model on a quantum Monte Carlo simulation, there's a sign problem. Okay, so which means that for this system, you have to resort to other kind of numerical tools to study it. Okay, but fortunately for us, there's a different set of Kramer's doublet, which is called a dipolar octopolar Kramer's doublet, which is neodymium 3+ and dysprosium 3+ fall into this class. And the effective model for this type of doublets is actually very simple. So this is basically you have this direction-dependent exchange. Okay, and this one we can do simulation. Okay. Yeah, I just want to mention that here these operators are in the local axis, and this is in the global direction. Okay. So as the previous speakers already mentioned, this Kagome lattice. So I learned a couple of years ago that this Kagome is actually is a Japanese word, and it's describing this network of basket. Okay, for a particle lattice, if you look at the lattice from along the 1-1-1 direction, you'll find that this particle lattice is actually composed of a Kagome layer, triangular layer, Kagome layer, and triangular layer. Okay. So when you apply for this particle material, if you apply the magnetic field along the 1-1-1 direction, when your field is big enough to pin these spins in the triangular layer, but not so big that the Kagome layer spins can still fluctuate, then you'll reduce the system from 3D to layer Kagome layers. Okay. So what happens to the ice rule? Okay, say if you're in a spin ice state, but you apply a magnetic field, you pin the spin so the spins on the triangular layer can only pointing along the field direction. Okay, so we know, I mentioned that the ice rule for the tetrahedron is 2 in 2 out, but you already assign one spin out. So basically, what was left will be just 2 in 1 out. Okay, and depends on which sublattice you're in. So you'll be in 2 in 1 out or sorry, it's 2 in 1 or 1 in 2 out. So there's a typo here. Sorry. Okay. So you can also estimate the residual, the entropy, and because of this spin is pinned, so the residual entropy is reduced. Okay. So here I show just the Pauling estimate, but in the in this Kagome system, this residual entropy can be exactly calculated. Okay, right. So if we take that this XYZ model and just reduce ourselves in the Kagome plane, but just you take this XYZ model and apply a field along the 1-1 direction, and this is the model that you'll get when you constrain yourself on the Kagome plane. So you have a field, and you have these different types of hopping terms. Okay. So for the moment, we're going to focus on just without this hopping term, but with only this pair creation term. So it would be just S plus, S plus, S minus, S minus. Okay. So Roger Makel's group did a Monte Carlo simulation, and they found this, that they map out this phase diagram. Okay, so here is a J plus minus, this parameter, and this is the H. So what they found is that they found there are two lobes. Okay? There are two lobes. And these two lobes, they term this as a QKI state. And in this state, they don't see any long-range magnetic order or any kind of symmetry breaking states. Okay? So they couldn't see magnetic order or like a bound correlation, and there's a gap ground state, and there's no long-range order, and then they speculate that maybe this is a Z2 quantum spin liquid. Okay? And there's because of this, if you do if you take this model and try to write down the gauge theory kind of a description, and you can say that there's a U1 gauge theory, and the pair of spinors can condense and get Z2 spin liquid. Okay. So again, this is the model, and from field theoretical, more careful field theoretical analysis by Yiping and Mike Hermely, they think that the phase diagram, just if you could focus on one lobe, should look like this. Right? So you have this QKI state, and this is the Z2 liquid, and you have VBS. Okay? But how can we be sure this is really a Z2 spin liquid? Okay? If from the tutorial by Subhro, we know that it's not only that there's no symmetry breaking is not enough to say this is this topological Z2 liquid state. So we went on to measure this topological entanglement entropy, and which we can do in the Monte Carlo simulation. Okay. So this is a one slide summary of how far, what it means in terms of topological entanglement entropy. So the entanglement entropy for the classical for these systems, normally you have this area law piece, which is proportional to the boundary of your subregion, but there will be a constant piece. Okay. This is described will characterize the topological entanglement. Okay? So by computing the entanglement entropy of some subregions, and you can subtract all this area contributions, then you get you can extract this constant term. And if the system has is a Z2 liquid, this gamma should be log 2. Okay. So in Monte Carlo simulation, what we measure is a second Renyi entropy. Okay. So what we use is SSE and with a replica trip, and here's the results. Okay. So if this the system is, if this state is a Z2 liquid, we expect this as a function of temperature. When beta increases, you expect this go up to here. Okay, and this is what the expectation. Okay, but to the lowest temperature and to the larger systems that we can calculate, so we get a value which is far below this expected value. Okay, it's not even close. Okay, so from this we can conclude this is what been called a QKI state is not really a Z2 quantum spin liquid. Okay, but if it's not a Z2 quantum spin liquid, yeah. Yes. Yeah, but it's not clear because we did a scaling, but we tried another method. Okay, so another method is we can use tensor network and directly get the entanglement entropy. But we didn't try a very large system size, but it seems that it is consistent that this extract to 0. Okay. So if this is not a Z2 spindle grid, is it what kind of state it is? Okay. So one thing we set out to do is we start to measure this thermal entropy. Okay. Because if we expect that if the temperature is cooled down, then there's a transition from the classical Kagome Ice to something else, your entropy should change, right? So to our surprise, that we calculate the thermal entropy and down to about 200 beta equal to 200. Okay. The system. Okay, the entropy is still looks like a classical Kagome Ice, and this is the residual entropy for classical Kagome Ice. Okay, and you have exact numbers you can get. Okay. So this is really puzzling. Okay, so imagine that we start from a quantum model. We did all the quantum simulations. And we did a careful analysis to make sure that we were in equilibrium, but still we see something very classical. What's going on? All right? Yes. Okay, so I'm going to talk about it. Yeah. We start from a classical Ice manifold. Okay. Let me just go through the degenerate perturbation theory. Okay, so what we did is we started from a classical. So this is basically a classical Kagome Ice manifold. And we start adding these quantum terms. Okay. And remember, my original Hamiltonian, I have two terms. So one term is this pair creation term, and another term is this hopping term. Okay. So we're going to do it separately and see what's the difference between these two. Okay. And in this case, we can use this hexagon. The number of upspins in hexagon to uniquely determine what's the state for these neighboring spins. Okay, because we're actually only in this because of this finite spin Zeeman field, we're only in this 2 up 1 down manifold. Okay, so we can just use this number of upspins as a classification for these different states. Okay. So for this, we have 5 possible hexagon configurations. Okay. So we did the degenerate perturbation theory, and it turns out for this model, if you have only this term, you need to go up to 6th order. And if you go up to 6th order, then not only you have this familiar ring exchange term, there's a series of terms that are the same order, but there's like diagonal processes. And these are kind of the potential energy term you get. Okay. Yeah. So let's look at more carefully what are the processes. So we have these diagonal processes. And this process, basically, you want to come from this state. Okay, so if n equals 3, and you want to do a ring exchange, so basically you hop your upspin here, and go to here. Okay, but because of this peculiar Hamiltonian, to get so to do this hopping, I need to S plus, S minus, S plus, S minus, S plus, S minus. But to construct this operator string from this S plus plus S minus minus, the only way I can construct is go out of this hexagon and come back. So S plus plus, minus minus, and so on. So this is the sixth order perturbation that I need to do to get this this ring exchange of this this hexagon. Okay, but because we have to go to the sixth order, there are terms which is at the same order and which are diagonal. So for example, if I take this n equal to 4 state, and I can apply these operators. So this just S plus, S plus, S minus, S minus, and I come back to the original state. Okay. And so that's actually the key, okay, leading to such a system continue to behave classically. We can look at the other more familiar process. Okay, so let's just add this from the classical Hamiltonian, but add instead this S plus S minus hopping kind of type of term, and so to have this kind of ring exchange process, all you need to do is just go to the third order, because you can have a string of S plus S minus S plus S minus on the hexagon. And at this order, all these other diagonal terms are actually just constant. Okay. All right. So if you analyze this Hamiltonian, then if this dominates, then you expect there to be a VBS state, and that's been confirmed using Monte Carlo. Okay. So now, what's going on in this system? We have a rough picture. So you can think of the system star from a classical Kagome Ice manifold, but you start adding these quantum perturbations. So if you have only this term, or have only this term, you start adding this this ring exchange term, and the ground state, if this dominates, you expect it to have a valence bound solid state. Okay? But for this Hamiltonian, we can continue to add this diagonal sort of potential energy. Okay? So with this, and I forgot to mention, the sign of these coefficients are actually the same. So actually they are competing of the same sign. So they are competing. And the competition actually leads to this restoration of this this degenerate spectrum. Thus, we see all this classical behavior. And so initially, you have if you transition into a VBS state, you have a huge gap. But because of this term, the bandwidth of your states becomes extremely small, and you need to go to a super low temperature to see any quantum behavior. Okay. So these are from degenerate perturbation theories, but we can also look at our simulation in the Monte Carlo. Okay, so what I'm plotting here is this fraction. So this P here is a fraction of hexagons with n up spins. Okay, so as you can see, for this case is that I turn off this part, and this is been studied before. We expect it to go to a valence bound solid phase, okay? Which means that n equal to 3 hexagons should dominate. And as you can see that at high temperature, you start with your configuration, but at some point this n equal to 3 hexagons become important. Okay, this ratio rises. Okay, but if in our case, we get rid of this term and we have keep only this term, and this hexagon fraction surprisingly remain constant. So they're not changing. There's no temperature dependence of this hexagon fraction. Okay. So to further understand what's going on, so we play around with this the effective Hamiltonian that we derived, but since we understand it's the competition between this ring exchange type of terms and this potential type of terms. So we decided, okay, let's tune this. Let's just give you the tuning parameter, okay? Because our effective Hamiltonian is coming from a degenerate perturbation theory, but in this simulation, the parameter sets are actually far away from this degenerate perturbation theory is valid. Okay, so let's see what happens. Okay, so the first limit we discuss is that this alpha goes to infinity. Okay, which means that you have only this diagonal part of the term. Okay, so since this is just a classical potential energy, basically all the classical Kagome Ice states are the eigenstates. Okay, but interestingly, the spectrum shows that there's a threefold degenerate state, and which are dominated by this n equal to 4, and these are so. I hope you can see it. So there are darker sides, which is up the down spins, and lighter sides are up spins. Okay, and they form this pattern. Okay, and this pattern is actually just called one by one or the charge order state in the classical Kagome Ice. Okay, and we go to the other extreme. So we turn off this diagonal part of the Hamiltonian. And what we found is actually the ground state. Okay, we expected it to be some kind of VBS state, and but due to a finite size effect, there's a small gap. But we can look at so here what I plotted is the x-axis is the index for all these classical states, and this is just a probability distribution. Okay, so dominate states, all these states are actually picked up with n equals 3 hexagons. Okay, and these dominant states are just these classical configurations, which corresponds to this square root 3 by square root 3 order state. And so this, if you think of this, there's a resonance, and then that will lead you to a valence bound solid state. Okay, so with this understanding, we can start thinking, okay, if I tune the alpha, what would happen? Okay, so this is the spectrum. So alpha 0 is here. Okay, alpha large is here, and so you can see when you tune alpha, so the states start to pile up. Okay, so this is a very small number. Okay, but you can see that the states start to pile up, and more and more states come into close to a ground state around here. Okay, so what we did here is that, okay, let's just set a threshold and start counting the number of states below this red line here. Okay, and we see that the number of level below this threshold, okay, so this is an arbitrary threshold. Okay, it start to peak, okay, at certain alpha value and then goes down again. And so this competition between this diagonal and off-diagonal processes actually compress the bandwidth of your states. Okay, and also from this finite size ED study, we found that okay, near here, what also happens is that you have some kind of level crossing. Okay, you have some kind of level crossing for the ground state. So that's what we think is really happening. So it's really the competition of these two type of quantum process. They cancel each other out, and such that the system, the quantumness freezes out and remain classical down to this very, very low temperature. Okay. So with this understanding, we can ask ourselves, okay, let's go back to the original model and just add this hopping term, right? This hopping term, and we expect because this term at some point, this third order perturbation theory ring exchange term should dominate. So you should start seeing VBS, and that's actually what we see. Okay. So this is what we get for our full phase diagram. Here plotted. So if you do this full simulation, this hopping and this is the strength of the pair creation. Okay, we find that this peculiar state, quantum Kagome Ice state, is actually just when you tune your J plus minus very small, or we don't really know if there's a transition, okay, because we didn't do a very systematic study, but we know that at some point this state becomes a VBS, and the physical process becomes the dominant of this lower order ring exchange term. Okay. And is there any physical system might be relevant? Okay, so Gang mentioned that this neodymium zirconate system. So the ground state for this system is all in, all out state. Okay, so it's not very interesting. But recently there's a claim that if you look at the dynamics, okay, they claim that in the neutron experiment they see that there's a dynamics Kagome Ice kind of mode, but there are some caveats which is not quite understood is because of its physics or because of the experiments. Okay. With this, I'm gonna draw a conclusion. So we found that this QKI state is not a Z2 quantum spin liquid. But the interesting thing is actually the system remains very classical, and we also did a classical simulation of the corresponding classical model, and we basically reproduce everything you see in your quantum Monte Carlo. Okay, and this behavior is actually, we understood, is because of this competing quantum processes. Okay, but for the moment, we cannot say anything about the true ground state of this model. Okay, and we don't think that it's possible to probe it numerically further or experimentally, because this is really subtle. Okay, and the energy scale is so small that any other perturbation will just destroy it. Okay. Is there a relevance in this material? It's yet to be clarified. Okay. With this, thank you for your attention.
Thank you for your talk. Any questions? We had a lot of questions during the talk, but any further questions?
Entropy very low temperature. So did you calculate the topological entanglement entropy in the phase VDS?
No. So we can only calculate the topological incandescent entropy around this temperature.
Difficult to.
Yes.
I see.
Any other questions?
Hi. So in this comparison that you were showing between the occupation of the upspins in a hexagon, suppose I start from the J plus minus. Yeah. So suppose I start from the left panel and then gradually, or maybe the right panel and gradually turn on J plus minus. So do you immediately see this crossover shifting towards lower temperature?
Okay, so one thing is that don't read this crossing too seriously, because this is misleading.
Sure.
Because you should look at where this start to deviate.
Yeah.
I forgot to mention, this is the estimated energy scale from just the ring exchange. Using the probability. Okay, I do have a figure, but I don't have it in my slide. So actually, if you have both, you see something similar to this one. But this actually get pushed down to, I mean, the behavior get pushed down to lower temperature.
Okay. Thanks.
Any other question?
So in your calculations of the corner entropy, it initially starts at 0 and then picks up and stays at 0.1, right?
Yeah.
Do you have any understanding of that?
So one thing we're thinking is might be corner contribution. Okay, so because we are doing the finite temperature calculation, okay, so this cancellation just cancel out the leading term, but there's also a higher order term, and that might be a contribution. And because if you have a gapless system, then you have it's clearly you can see this corner contribution. But since the gap of our system is so small, right, and the temperature that we can went down is not small enough, so this might be just these subleading corrections. Yeah. But we don't know for sure.
The sudden pickup in the.
Oh, okay. So the state is evolving. So at this high temperature state, you don't expect. It's basically just a paramagnetic state. Yeah.
Any other question? If not, let's thank our speakers again.